Okay, 3.4, velocity and other rates of change, part B. So particle motion initially means when t equals 0, and t, of course, is time. At the origin means when the position, or s of t or x of t equals 0, and at rest means velocity is 0. So velocity v of t equals 0. All right. If the velocity of the particle is positive, then the particle is going to be moving to the right, also known as forward. Now, if the velocity of the particle is negative, then the particle is going to be moving to the left or backwards. Depends on what they say in the question. Okay, in order for a particle to change direction, the velocity must change signs. And what I mean by change signs, when we look at the graphs, it'll be easier to determine what you're talking about. But the signs are from negative to positive or positive to negative. So if one part is positive and then it changes to negative, it changed signs. That means the particle changed direction. Okay, the relationship between velocity, acceleration, and speed is illustrated. Oops, that's misspelled. Is illustrated in the table below. Okay, so when acceleration is positive, right, that's the first one right here, and velocity is negative, the object is going to be slowing down. When acceleration is positive, but velocity is also positive, the object is going to be speeding up. When acceleration is negative, and the velocity is also negative, then the object is going to be speeding up. And when acceleration is negative, but velocity is positive, then the object is slowing down. If you really take a look at the table, basically, when signs of both acceleration and velocity are the same, then the object is speeding up. So if they're both positive, like positive 6 and positive 8, then the object is speeding up. Now, when the signs are different, when the signs of velocity and acceleration are different, then the object is slowing down. Okay, more relationships here. If I can get this to come down. Oh, hee. Extend. Okay, the relationship between velocity and acceleration. All right, whenever velocity is increasing, so basically on a graph it would look like this, like it's moving up towards the right. My slope is going to be greater than, right, 0. So therefore, acceleration is positive, and all positive numbers are greater than 0. Okay, when velocity is decreasing, basically it's going to be looking like this, right? Like it's coming down towards the right. My slope is going to be a negative number, right? My slope is going to be smaller than 0. So the acceleration is going to be negative. And then when velocity is constant, if you think about it, constant velocity is a straight line, a horizontal line, in which case my slope is going to be 0. And if my slope is 0, then acceleration is 0. Because remember, acceleration is the derivative of velocity. Velocity. I know it's a lot of information, but you get used to it. Okay, next. Reading a velocity graph. So here I have a velocity graph. Notice how there's like a bunch of little peaks. It's really weird looking, right? Okay. So example 1, this is graphical. And I'm going to have to keep coming back up to the picture. So Just bear with me. Maybe I make it a little bit smaller. It'll be doable, right? Okay. From the velocity time graph above, please indicate the time or times when. All right, first one. The object is moving to the right. Okay, so the object is moving to the right when velocity is positive. If velocity is positive, then the object is moving to the right. Another way of looking at it, is the parts of the graph above the x-axis. So graph above x-axis. That's another way of looking at it. Anything above the x-axis. I know this is in seconds and meters per second, but basically this is still the x-axis. So anything above. All right, so when is the object moving to the right? So let's see. Here, these are all positive, positive. Oh, that's negative because it's below the x-axis. Negative, negative. 0 is not positive or negative. So, oh, here we go. Positive, positive, positive. Okay, so all of this red stuff, that is when the object is moving to the right or forward. So I would say, okay, from 0 to 2, the object is moving to the right. But then I would also say from 5 to 12. Oops, forgot my less than. Okay, these are intervals. All of my, all of my answers except for one are going to be intervals. Okay, so next, the acceleration. Okay, so indicate the time or times when the acceleration is positive. So acceleration is going to be positive whenever the velocity is increasing. Okay, so whenever the velocity is increasing. So basically, it'll look like that. So let me go ahead and erase this red stuff. Okay, so let's see. Here, oopsie. Here, the velocity is increasing. And then now we're decreasing, decreasing, decreasing. Right? All of this is decreasing. And then, oh, right here, we increase a little bit again. And then flat. And then, ooh, increasing again. And then flat. And then decreasing. And then flat again. And then decreasing again. So that's it. Only at those 3 intervals. So from 0 to 1, 0 to 1, from 3 to 4, and of course the last one's barely gonna fit. From 5 to 6. 5, well, hold on. Alright, I managed to squeeze it in there. 5 to 6. Alright, please indicate the times or times when the acceleration is negative. Okay, so acceleration is going to be negative whenever velocity is decreasing. So kind of like the one before, only this time it's going to look like this. It's going to come down. So I can leave the green stuff because now I'm going to focus on coming down. So here, this is coming down. Okay, obviously the green stuff and the flat parts of the graph, like right here between 4 and 5, not going to worry about that. Increasing, here's flat again. Oh, look, decreasing. So here's another one. And then I have some more flat stuff. And then now more decreasing. So there are 3 intervals for this one as well. Let's see if I can fit these in. So from 1 to 3. From 1 to 3. Let's see, from 7 to 8. From 7 to 8. And then from 11 to 12. 11 to 12. Okay. Next, when is the object speeding up? Okay, so this is where those charts will help you, right? Well, the charts should have been helping for the last two as well. This object is speeding up whenever velocity and acceleration have the same signs. Okay, velocity and acceleration have same signs. So when they're both plus and when they're both minus. So that's actually going to require looking at this graph and doing something with the graph. If you look at the next one, they want to know when the object is slowing down, and that's going to be whenever velocity and acceleration have different signs. So what we're going to do is we're going to take the graph and we're going to figure out what the velocities are and what the accelerations are. And then we're going to compare them. So, okay, I'm going to take the graph, and I guess I'll do velocity in red. So I'll do all the velocities up here, and then I'll do the acceleration part in blue down here. So let's see. I'm going to make this thinner. Okay, so velocity, I want to know when it's positive and when it's negative. Okay, so let's see. From here to here, my velocity function is above the x-axis, so it's positive. But then from 2 to 4, it's below the x-axis, so it's negative, right? And those y values are negative, or the meters per second, they're negative. Okay, from 4 to 5, that's constant. It's actually y equals 0, so my velocity is 0. My object is at rest. From 5 all the way to 12, my velocity is positive because these are all positive y values. Okay, so I figured out where my velocity is positive, negative, positive. I'll even write, that here it's at rest. All right, so now I'm going to go ahead and do the same thing, but for acceleration. So okay, acceleration. Now, acceleration depends on the velocity. Remember in the chart up there, acceleration is positive whenever velocity is increasing, and negative whenever velocity is decreasing. And then whenever velocity is constant, acceleration is 0. So we turn to the graph. And okay, so velocity is increasing from 0 to 1. So therefore, acceleration is positive. Okay, now velocity, my velocity graph, because this is my velocity graph, it's decreasing from 1 all the way to 3. Since it's decreasing, acceleration is negative. All right, from 3 to 4, right here, I see that the velocity is increasing, so acceleration is positive. And then from 4 to 5, velocity is constant, so acceleration is going to be 0. From 5 to 6, my velocity is increasing, so once again it's positive. From 6 to 7, I see that my velocity has become constant again, and therefore the acceleration is going to be 0. From 7 to 8, this is really tedious, isn't it? From 7 to 8, it's decreasing, so acceleration is negative. And then from 8 to 11, my, what do you call it? Velocity is positive, right? So acceleration is or what am I saying? It's constant. I'm sorry. Velocity is constant. So acceleration is 0. And then from 11 to 12, the last little bit, the velocity is decreasing, therefore acceleration is negative. Okay, so now that I have it all mapped out, basically, what I'm going to do is I'm going to compare, and I need to figure out, okay, so for like the first one, where it says the object is speeding up, for this one, I'm looking to see where the signs are the same. So what I'm going to do is I'm going to compare my pluses and minuses up here to my pluses and minuses down here. And I want, obviously, like the first interval here, from 0 to 1, velocity is positive all the way to 2. But acceleration is only positive all the way to 1. So at least in this little interval, their signs are the same. So I'll just highlight it right here. So for this interval, the signs are the same. Right? Positive, positive. Okay, for the next, from 1 to 2, velocity is positive, but acceleration is negative. So no. Okay, from 2 to 3, velocity is negative, but from 2 to 3, acceleration is also negative. So here's my other little interval where their signs are the same. Okay, so you just keep going. Let's see, I have negative, positive. It's resting, and so it's 0. And then for the rest, from 5 all the way to 12, velocity is positive. So the only place acceleration is positive in that interval is right here from 5 to 6. So this is, oopsie, didn't like what I was doing. So this is what I've got. Those three intervals are the only places where velocity and acceleration have the same signs. So therefore, in those three intervals, the object is speeding up. So now I'm just going to write that down. All right, so I wrote down the intervals. Now I'm going to do basically the same thing for the next one, only that this time I'm supposed to be paying attention to where the signs are actually different. All right, so let's see. From 1 to 2, I see that velocity is positive and acceleration is negative. So right here, the signs are different. From 3 to 4, velocity is negative and acceleration is positive. So there the signs are different. Oops. So that means that the speed is going to be slowing down. From 4 to 5, rest and 0 doesn't count. 6 to 7, 0, no. 7 to 8, my velocity is positive, right? But my acceleration is negative. And then from 8 to 11, 0, so that doesn't count. And then from 11 to 12, my velocity is positive, but my acceleration is negative. So these four intervals are where the object is slowing down, so I'll write that down. All right, so I wrote that down. Next, the object is standing still for more than an instant. So I need to figure out where is this object standing still for more than an instant. And the locations where the object is not moving is whenever velocity is 0. So all I have to do is look up at the graph and be like, okay, where's the velocity 0? Well, here's 0, right? So what part of the graph is actually on there? Oh, look, right here, from 4 to 5. So from 4 to 5, this object stopped moving. So I'm just going to put from 4 to 5 in that interval. Okay, I'm going to have to move this. Next, the object changes direction. Okay, so the object changing direction depends on where velocity changes signs. So that means when does velocity go from being negative to positive? Or positive to negative, vice versa works as well. Okay, so I look at the graph and, well, let's see. I'm going to do this in black. All of this right here is positive, but then right here at 2, it goes underneath the x-axis, so it becomes negative. So at 2, so there's one answer. At t equals 2, my velocity changes signs. And then, so here's negative, right? And then I have, well, suddenly I'm no longer below the x-axis, I'm right on it. because the object is at rest. But then it becomes positive. So it did change signs. It just took a while longer than just an instant to change signs. So I'm just going to go ahead and write, okay, at t equals 4, it changed signs. But really, 0 is not positive or negative. So I can say between 4 and 5. We'll just leave it like that for now. All right, next and last one, right? Yes. The speed is the greatest. When is the speed the greatest? And this is graph the object speed. Okay, so I'm going to have to erase that. Okay, well, first of all, speed is the absolute value of velocity. So that means that although this graph has parts that are negative, my speed graph can't. That's the whole point of absolute value. So anything that is negative, for example, this part down here, needs to become positive. So what you do is you just flip it up. Flip it up and that's your graph. So let me erase that. So here, so this was 3 negative 0.2. So now it's going to become 3 positive 0.2. And then this is my speed graph. This, that, this, up like this, like that. I'm basically drawing over the old one, except for the part that I fixed. And then this wouldn't be here at all. So there's the speed graph. Okay, so you have to do that on your homework. Now you know everything that's negative needs just to be flipped up. And that'll be a positive version of it, and therefore it'll be your speed graph. Because speed and velocity are basically almost the same thing. They are different, but graph-wise, it's basically the same thing. You just have to make everything positive. Okay, now, we're supposed to find where the speed is the greatest. Okay, look at the graph and figure out where the biggest y value is. And of course, it's right here. So speed is the greatest between 6 and 7. And that's it. Because that's the tallest place, right? So between 6 and 7. Okay, moving on. Okay, example 2. We're doing this now numerically. So last time was graphically, now it's numerically. A particle moves along the x-axis so that at time t, its position is given by x of t equals t cubed minus 6t squared plus 9t plus 11 for an interval from 0 to 5. Now notice how the position function is being called x of t. Okay, s of t, x of t, they're the same thing. They're interchangeable. They will use both. Okay, so part A. At t equals 0, is the particle moving to the right or to the left? Explain your answer. Okay, so in order to figure out if the particle is moving to the right or to the left, basically what you're asking is velocity positive or negative at this t equals 0? Okay, so that's basically what we're asking. So to figure out if velocity is positive or negative, you take the position function and you derive it. And the derivative of position function is velocity. Okay, so the velocity function is 3t squared minus 12t plus 9. Okay, so I want to know if it's positive or negative at 0. So I'm going to plug in 0. And I'm going to get 0 minus 0 plus 9. So my answer is a positive 9. So therefore, the particle is moving to the right because it's positive, since v of 0 equals 9, which is positive. So I'll write that down. So there you go. That's my explanation. The particle is moving to the right since v of 0 equals 9, which is positive. Obviously, if it had been negative 9, then I would say, oh, it's moving to the left, right? Okay, B. Okay, B says at t equals 1, is the velocity of the particle increasing or decreasing? Explain your answer. So basically what we're saying here is acceleration positive or negative. Because once I figure out if it's positive or negative, then I can tell you if velocity is increasing or decreasing. Okay, so what we're going to do is we're going to take the position function And we're going to derive it two times. Because the second derivative of the position function is the first derivative of velocity, which is acceleration. Okay, acceleration is the second derivative of position, or the first derivative of velocity. So acceleration, let's see, my velocity function is up there, so 2 times 3, that's 6t minus 12. And I want to know, is it positive or is it negative at t equals 1? So I'm going to plug in the 1, and I get negative 6. So voila, it is negative. And whenever acceleration is negative, that means velocity is decreasing. So I'll write out my explanation now. So there's my explanation. At t equals 1, the velocity of the particle is decreasing because v prime of 1, which equals a of 1, equals negative 6, which is negative. I know, redundant, but just in case. Because you do have to do explanations on FRQs, and these are valid explanations. All right, C. Okay, C says find all values of t for which the particle is moving to the left. So basically what we're doing is we're going to figure out where v of t is less than 0. Okay, so a way to figure out where v of t is less than 0, which means negative, I actually have to figure out where my velocity function might have changed signs. And the location where my velocity function might have changed signs, or at least two of them, is where my velocity is equal to 0. So I'm going to take the velocity function. I'm just going to write it over from up there. 3t squared minus 12t plus 9. Okay, so I'm going to take my function and I'm going to set it equal to 0. So let's see, let me set it equal to 0, and I'm going to factor. I see that they all have 3's in common, so let me just pull out a 3. So t squared minus 4t plus 3. Okay, so let's see, I need two numbers that multiply up to positive 3, but add up to negative 4. So t minus 3 and t minus 1. So they multiply up to positive 3, but they add up to negative 4. And then I get my two values. I get t is 3 and t is 1. So now basically what I'm going to do, and there's a reason why this example is numerical, I'm going to make myself a little table of the values where my function, my velocity function, not the position, where my velocity function is going to be, well, might change signs, where it could possibly turn into negative. Okay, now here's the important part that people always forget or have problems with. I just found these out, right? But these aren't the only places that I actually have to check. I also have to check my interval. Up here, remember this? From 0 to 5? So I'm going to make my table, and I'm going to use the t values of 0, of 5, of 1, and of 3. Okay, so there's my table. I used my two numbers that I found by factoring, and I used the endpoints on my intervals, or interval. So 0, 1, 3, and 5. So now what you would do is you would plug in 0 into the position function. So let's see, 0 minus 0 plus 0 plus 11. So that's 11. All right, that's easy enough. Then you would plug in 1. I'm confident that I don't need to show you how to plug in numbers. When I plug in the 1, I get 15. When I plug in the 3, I get 11. And then when I plug in the 5, I get 31. So now I need to figure out, all right, when is this particle moving to the left? And you can do that very easily by creating some kind of little graph, right? So at the beginning, at t equals 0, this function was positioned at 11. So let me make myself a little number line here. Here's 11. And then eventually it went to 15. And then it went back to 11. Oh, look, it went back to 11. Huh, could it have turned? And then the last one, it ended up at 31. So you kind of just want to mimic what happened. So at t equals 0, it already was at 11. and then it moved to 15, right? But then it moved back to 11. It turned around and moved back to 11. And then, oh look, it went up to 31. In order to do that, I'm gonna have to turn around again. So, we're supposed to be looking for, find all the values of t for which the particle is moving to the left. Okay, so the only place I see that it moved to the left is right here. So, the particle was moving to the right from here to here, right? It's moving to the right, and then all of a sudden, it went from 15 back to 11. So, to answer my question, find all values of t for which the particle is moving to the left. What I'm going to say is, and I'm going to write it out as a sentence just in case we need it later. The particle is moving to the left for the interval from 1 to 3, because this is where v of t, which is my velocity, is less than 0. And I'll write that down now. Alright, so there's my explanation. Alright, part D. Find the total distance traveled by the particle over the time interval from 0 to 5. So total distance traveled. What I'm doing there is I'm trying to figure out how much or how many, what is this, in feet? Oh, there aren't any units. So we'll just call them units. How much was actually traveled by this particle? Now this is tricky because people have the misconception that distance is just from point A to point B. But the question is, how did you get from point A to point B? Okay, real quick example. You don't have to write this down, but just look. So this is my house, right? And this is school. And if I take a straight shot there, let's say it's 10 miles. Okay, well what happens if I didn't take a straight shot there? What happens if one day I decide that I'm going to go to the store and then I'm going to pump gas, right? So this is my alternate route. And let's say that this is 5, and then this is 7, and then this is 5. Well, the total distance traveled certainly changed from the first scenario to the second scenario. Okay, in the first scenario, when I just went from home to school, distance travel was 10 miles. But in the second scenario, when I stopped at a store and I went to get gas before going to school, well, 5 plus 7 plus 5, that's 17 miles. Okay, so you kind of think about that when they ask you for total distance. It's not just, okay, let's see, the interval, the end of the interval is 5. So from 0 to 5, I need to figure out how much was traveled. Because it's basically just displacement. I don't want to know how much was being displaced, how much the particle was displaced by. I need to know how much the particle actually traveled. And if you remember back to part C, it turned to the left and then came right back. So if you look at part C, although this looks like it traveled 20 units, it actually didn't, because from 11 to 15 it traveled 4, but then it traveled 4 to the left, so that right there is 8. And then from 11 to 31, that's the original 20 that I had marked down here. So the actual traveling time or distance, sorry, was 28. Okay, so I'll show you how to do that now. What I'm going to do is I'm going to make two tables. One is the long way, one is the short way. Pick your poison. Okay, so if you were listening, I just basically explained what the total distance traveled was. You can use that little chart that we made in part C, this right here. Like I said, from 11 to 15, that's 4, but then from 15 back to 11, that's another 4 units. And then again, from 11 to 31, that's 20, so that is 28 units. And that was the total distance traveled. So you could make one of these. Obviously, the 20 isn't correct, right? Or you can just make tables. The one on the right, notice, I'm using the same values from here. This is the same table, just that this is horizontal rather than vertical, right? You can make it vertical. I just figured there'd be more space if we did it horizontal. This This is the long way, in case you're like, oh my god, which values am I supposed to use? You could just use all of the values in the interval from 0 directly to 5. So 0, 1, 2, 3, 4, 5. And you could find the distance this way. Of course, there are more numbers to plug in on this side versus this side, right? So we already know what we got for 0, 1, 3, 5, so I'll fill those in. And then for 0 through 5, you could just plug in the ones we don't have values for. So I'll fill that in now because I shouldn't have to teach you how to plug in stuff. All right, so basically, I want to know how many units were moved for every single second up here. So I'll start with the one on the left. From 0 to 1, we moved 11 to 15, so it's 4 spaces, or 4 units. From 15 to 13, it moved 2. Backwards, but that's okay. It's still 2 spaces. From 13 to 11, it moved 2 more backwards. From 11 to 15, forwards, 4 spaces. And from 15 to 31, 16 spaces. So what you would do is you just simply add them, or units, sorry, unit spaces, whatever floats your boat. And I get 28 units. And it's a long way because there's more numbers. With this one over here, you would use the interval, the ends, right? This is the end, and then this is the end. And then the two numbers in between, if you recall, we got them from part C up here. Because what we did was we took the velocity and set it equal to 0. And we figured out where would velocity actually change direction. And when it equals 0, those are potential change direction points, or t-values. So I'm going to do the same thing. From 11 to 15, that's 4 points, or 4 units. From 15 to 11, that's 4 units again. And from 11 to 31, that's a total of 20 units. But you add them up, and you still get 28. So the total distance traveled by the particle is 28 units. And this is all numerical. I did this with tables, right? Part A and Part B was very much analytical, right? But Part C and Part D was all tabular, numerical. Alright, so here's something new. It's called the intermediate value theorem. And sometimes I'll refer to it like that, IVT. If f is continuous on the closed interval from a to b, and f of a does not equal f of b, so that means they are different values, the y values are different, and k is any number between f of a and f of b, then there's at least one number c in the closed interval ab such that f of c equals k. And you're like, eh? So here's a picture of the graph, of a graph, that works perfectly with this theorem. Notice how f of a and f of b, so the y values, this would be f of a, and pretend that's straight, this would be f of b. They're not the same. Okay, they're totally different. Now what they're saying is that there's a number called k between f of a and f of b. So let me find some number called k, and I decide that I'm going to call this k right here. There's a number k somewhere in between those two y values. And since k is in between those two y values, what this theorem allows us to do is assume that there is a value called c, which is an x value. There is an x value in between a and b that belongs to k, which means if I plug it into the function, I get k back out. So basically, c is the x, and k is the y. So they're saying there's an x value in between a and b somewhere. And if I backtrack here, here's my c. There's a c in between a and b where I will get k. Of course, k has to be between the two y values, but that's why we work backwards, to make sure that it is. This theorem basically guarantees me the existence of this dude. Okay? As long as my y value, k, is in between my f of a and my f of b, then somewhere along the line of this graph, um, somewhere along the line, because it is continuous, there aren't any there aren't any gaps. There aren't any gaps. There must be an x that will get me that k value. Okay. All right. Okay. Here's a data table. They're giving me selected values for the velocity in meters per minute of a particle moving along the x-axis. The velocity v is a differentiable function of time. Okay, the reason they tell you this is because you need to be like, oh, it's differentiable. If it's differentiable, that means this function is continuous. Okay, so that's not just there for decoration. It means something. This function is continuous. There aren't any gaps. Okay, so there's my table. My times are 0, 2, 5, 6, 8, 12. The idea is if I had a function, if I plugged it in, if I plugged those values in, I would get negative 3, 2, 3, 5, 7, and 5. Okay, so A, at t equals 0, is the particle moving to the right or to the left? All right, so at t equals 0, let's look at that right here. Well, my velocity is negative. So whenever velocity is negative, my particle is moving to the left. So I'll write my explanation. There's my explanation. The particle is moving to the left since v of 0 equals negative 3, which is negative. I know it's redundant, but let's just make sure, right? Okay, part B. Is there a time during the time interval between 0 and 12? And if you notice at the table, it just goes from 0 to 12, so the whole thing. Minutes when the particle is at rest. Explain your reasoning. Or, sorry, explain your answer. I'm reading words that aren't there. At rest means that the velocity equals 0. If I look at my table, which is continuous, remember this function is continuous. It has no gaps. My velocity goes from negative 3 to 2. I erase this, get it out of the way. Right here. My velocity goes from negative 3 to 2. It only makes sense that in order to get from negative 3 to 2, velocity had to pass what number? Hopefully you're like, oh, it had to pass 0, right? And it did. It had to pass negative 3, negative 2, negative 1, 0, 1, and then finally get to 2. So, is there a time when the particle is at rest or the velocity is 0? Yes. I'll write down the explanation now. Okay, so here's my explanation using that intermediate value theorem. Now remember, the intermediate value theorem works on a closed interval. So my interval from 0 to 12 is less than or equal to. That means closed. Okay, so yes, there is a time when the particle is at rest during the time interval from 0 to 12 minutes. Since the velocity function is differentiable, it is also continuous. Remember, I said that in the beginning. Hence, by the intermediate value theorem, since velocity goes from negative to positive between 0 and 2, and that's when I was talking about this, it goes from negative to positive, so it has to pass 0 on the way there. It must go through 0, and v of t equals 0 means the particle is at rest. All right, part C. Okay, part C. Use data from the table to find an approximation. Approximation. You'll be doing this all year long. An approximation for v prime of t, and explain the meaning of v prime of t in terms of the motion of the particle. Show the computations that lead to your answer and indicate units of measure. So this is like a classic FRQ from the AP exam. They want you to approximate, they want you to explain what this thing that you're finding actually is, and of course they want you to show your computations, which means your work, and they want you to indicate the units of measure. Okay, so v prime of t, or 10. Well, v prime, what is v prime? Oh yeah, v prime is acceleration. Acceleration. Now I need the table, so I'm going to have to scroll back up, right? But what I'm going to do is I'm going to find acceleration at 10 seconds, which is v prime at 10 seconds. But the thing is, I don't have an equation. I have nothing to derive. So by approximation, we're going to approximate the slope because acceleration is a derivative of velocity. So basically, I'm finding the slope at t equals 10 seconds or minutes. I forgot what this was already. Minutes. So we're going to approximate the slope. We can't do it doing or using calculus, but we do know how to approximate slope some old-fashioned way, right? Look a little familiar with the y2 minus y1 over x2 minus x1. So first of all, I'm going to make a trip up to the table. I guess I could squeeze both of them in kind of right now. A little bit more. All right. So t equals 10. It's not even on the table. Nope, it's not. Where would it be? It would be here, right? 10 would be somewhere there. So I need to figure out how I can approximate the slope at t equals 10. Well, I'm going to approximate the slope using these two values, 8 and 12, and using their y values, or whatever I get when I plug those into my function, which I don't have. I just have a table. So I'm going to do 12 minus 8. Those are my x's or my t's. And then since I did 12 first, I'm going to do 5 minus 7. And that's good old-fashioned slope. And that's how you approximate slope in calculus when you don't actually have an equation, but you have a table of values. And you'll be doing this all year. Promise you that. So 5 minus 7 is negative 2. 12 minus 8 is 4. And I can actually simplify that, right? And I get negative 1/2, or doesn't matter where you write the negative, really. Now, my units of measure. I need to be careful with that. If I look at my table, well, time, right, which was the 8 and the 12, the bottom part, time was in minutes. So this is actually 2 minutes. Velocity, which is the top part of my slope over here, was in meters per minute. So meters per minute. So my actual answer is negative 1/2 meters per minute squared. Remember I told you acceleration is always going to be squared. Okay, so those are my computations. I found v prime of 10. Now I'm supposed to actually explain the meaning of v prime of 10 in terms of the motion of the particle. So here, v prime of 10 is the acceleration of the particle of the particle at t equals 10 minutes. And since the computations are there, you should be good. But if it makes you feel better, you can just go ahead and say, which is negative 1/2 meters per minute squared. Negative 1/2 meters per minute squared. Okay? And that's the explanation. Classic FRQ section problem. Okay. Sorry this took forever. I apologize. Velocities, there's a lot of stuff here. So I have an amendment to your homework. Please don't hit pause just yet. You're supposed to be doing number 23. Well, I want you to do the parts A through C only. You don't have to do D. And I had already asked you guys to add on number 9 and 21. Well, for 21, only do part B. I was looking over them and I'm like, This is really what I want you to do. I don't want you to do all the other stuff. And that's the amendment, I believe. Go ahead and do your homework, please. Try your best. I tried to give you all the information I could. That's why it's so long. Quiz next class on quotient rule and velocity, but it won't be like really hard velocity. Like you should know that the first derivative is velocity and the second derivative is acceleration. And if I'm telling you velocity is 0, find me with the times, stuff like that.